So welcome back. Now we are with this final wrap-up and outlook over the lecture. So I'll go over what we've done so far, just to make you feel good about everything you've learned in this course, and that will be useful for the future. And if you follow during the semester, then that knowledge will stay even after the exam. So we first saw in the introduction the motivation of a system like PostgreSQL. It's again to shield you from the complexity of storage. It offers a more abstract view over your database. So we saw that the database is the data itself. The database management system, that's the software, PostgreSQL, that's written in C++ or languages like this. And the database system, that's everything. The database plus the software that manages it is the database system. Okay, and system is the same meaning as in many others, right? You also have the notion of an ecosystem, environmental systems, and so on and so on, right? So there's plenty of systems, and database systems are one of them. Then we saw that data independence is the magic that separates the logical data model from the physical storage, the one I've just shown you with the pages and the records and the pages and the chunks and the files and the directories, but you don't see any of that. All you see is tables. We looked at the logical and mathematical definition of a table, and to summarize what we said, a relational table is a set of maps. A map is a record. Here we have 3 records, for example, 3 maps, but we have a few restrictions because otherwise it wouldn't be a table. So the first restriction is that relational integrity. So all the maps must have exactly the same attributes. Then you have this structure to the table. The second one is domain integrity, is the fact that in the same column, you must have the same kind of data. For example, year is always an integer, physicist is always a Boolean, and first and last are always strings. And then atomic integrity. Who remembers what it is, atomic integrity? The first normal form? Yes? No nested tables, exactly. Just atomic values, like this. All right, perfect. This is a summary of some of the standardized SQL types that you find in the system. These are the ones you can actually use in your create table statement. There's many of them, but there is a documentation that you can look up for that. And then we saw that when you have PostgreSQL, you can define the schemas of your tables, which columns you want to have, which types you want to have, what constraints you want to have, the primary keys, the foreign keys, and so on. Then you can populate the data, right? So we saw that you can create, modify, drop a table, and you can insert tuples. Tuples is just another word for record, map. It's all the same thing, just different words. So you can insert records, delete records, update records, and query records. That's the data manipulation language as opposed to the data definition language that operates at the metadata level. All right, then we saw the notion of primary key and foreign key, and that is all used to actually glue the table together, right? A foreign key is just a reference to another table. For example, you might have a list of tax returns with a social security number, and that links to the table that has the persons, where the social security number is a primary key. Okay, so this is the whole idea of joining multiple tables, because very often when you join tables, you are in fact going to join on the primary key and foreign key, right? In that case, they have the same name. I have house, so it would be a natural join, but you can also join if it's not exactly the same name, then it's just a theta join. All right, then we have plenty of queries. That's called the relational algebra. We can do the union, intersection, subtraction of tables, the set queries. We can select, we can project, we can rename a relational table or an attribute. We can join either with the Cartesian product. Careful with that, Cartesian product. If you crash the computer on exam day because you did the Cartesian product, we just move you to another computer. But you're supposed to be aware of that, right? You have to be careful not to crash the computer. Joining is fine. So if you join, that usually shouldn't explode the memory. So natural join, theta join, and shuffling queries, and we'll see in big data why it's actually shuffling, but it is grouping and sorting. It's basically manipulating the entire tables at a time when you group and when you sort. All right, and that's again a picture of joining, but who is now comfortable with joining and gets what it means? See some nodding. Okay, very good. This is very important, the notion of joining tables. Also with normal forms, the Boyce code normal form and so on, the idea that we decompose into multiple tables with the idea that we can join them back to the original table. Then you can group like this. That's typically in order to aggregate data and do summaries. You can sort. And then I told you that you have to distinguish between several kinds of computer languages. There is, on the one hand, the imperative languages, C++, Java, Python, and so on. These tell the computer what to do, it's instructions, as opposed to declarative languages, where you just say what you need, and the computer figures out how to do it, right? SQL is actually a declarative language. So that's here's what I want language. But of course, it doesn't mean the imperative languages are not useful, right? In fact, PostgreSQL is implemented in an imperative language, right? But it's done in such a way that you don't need to use it. You can just use a declarative language on top. So declarative languages are in a higher level of abstraction than imperative languages. And then we studied SQL, and now you know all of the secrets of SQL. You saw select, from, where, group by, having, order by, limit, offset. Now you know all the clauses in that order. So this is an example where we group and then we follow after the group by, we have a having, which is the same as where, but having is after the group by, where is before the group by. It filters the records, right? So this is an example. Then we saw all the ways you can do joins in SQL. In that case, it's a full outer join. And that means that for the poor little records on the left and the right that don't have any matches, we just complete with nulls, but we still include them in the output. That's a full outer join. Then you have the left and right outer join if you only do that on the right or on the left, and so on. All right, so the on here, because it's not the same name for the columns, means that it's a theta join. It's not a natural join. And then we looked into database design theory, which is directly connected to the idea of joins. Database design theory is a set of guidelines and principles that help you design good schemas. And this is done with normal forms. There's all kinds of normal forms, the first, the second, the third, the Boyce code, the fourth, the fifth, the sixth. So there's plenty of normal forms. And the higher the normal form, the better it is. But also the more challenging it is to actually constraint, right? And the idea is that the higher the normal form, the more you're going to have a lot of tables that are decomposed all over the place and that you join together. The lower the normal form, the less table you're going to have. So if you just in the first normal form, you can have just an enormous table with atomic values. And if you go higher, you're going to have more smaller tables. The idea, just as a rule of thumb of database design theory, is that you should have tables that make sense. Every table should do one thing. You have a table of people, a table of products, a table of orders. That's basically the idea behind all of that. And so we saw that the normal forms are additional constraints that come on top of your tables, on top of relational domain and atomic integrity. So we just add more constraints. And in order to define the notion of normal forms, there is a lot of math and concepts to learn. One of these is the concept of a functional dependency. That basically means that if you know the value of some attributes, then you know the value of some others. For example, if you look at the upper part of this, then A and B would give you D and E. But this is actually broken below, because here you have bar and foo bar in both cases, but the value of D and E is not the same. So in that case, the functional dependency AB determines DE would be broken, right? So it would be respected on the top, but broken below. And if it's broken at any place in the table, then it's completely broken. It's enough to be broken at one place for the functional dependency not to apply, okay? Then we had a lot of games with functional dependencies. One of them is to find the closure of a set of attributes. So we just start with a few attributes. And the goal is to add more and 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 more attributes. But there is a rule. We can only add these more attributes if we found somewhere a rule where we can find on the left those that we already have, and that allows us to add those that we find on the right. That I know you can do because 100% of you got it right when I asked the quicker questions. So I know you can compute the closure of a set of attributes. It's very mechanical to do and relatively easy. Then we saw that we can compute a minimal basis for a set of functional dependencies. What it actually means is that we just clean things up, right? It can really become a mess if you just put functional dependencies in there. So you can a bit simplify, and we saw that there's a few rules in order to do that. You don't need to look at really at the tables. You can just apply the rules like this. For example, this A determines A, we can remove that you see on the right, and so on and so on, right? So this is what we call the minimal basis. But there is the possibility that you have multiple minimal bases, right? If different people clean up the same set of functional dependencies, you might not end up with the same results, right? Just like there's several ways of cleaning up your apartment, right? You can decide where you put all the furniture. That's a bit the same. And based on that, so based on all of that, we then introduce the Boyce code normal form. Why this one? Because it's one of the easiest normal forms that there is. So this is why we focused on that one. So a relation is in Boyce code normal form if we don't have any undesired functional dependencies. And what I mean with undesired functional dependency is a functional dependency where the left is not a super key. In the Boyce code normal form, we only accept functional dependencies if the left is a super key of the table. Super key, again, means that the closure is everything. That's what a super key is. The closure of a super key is all attributes. All right. And so the nice thing about the Boyce code normal form, this is actually one of the other reasons why we like to use it, is that if you have your tables in Boyce code normal form, you won't have any update anomalies. This is the nice thing about the Boyce code normal form. We also saw that it's lossless in the sense that when you decompose, according to the algorithm I showed you, if you decompose a table that's not in Boyce code normal form, you decompose it into multiple tables that are in Boyce code normal form. If you do it respecting the algorithm, then you're not losing any data. What does it mean to not lose any data? It means that if you take the decomposed tables and join them back, you get back the original table. That's what it means to not lose any data. You store exactly the same data, whether before and after the decomposition. However, we do lose something. It's not data, fortunately, but we lose dependencies because some of the functional dependencies that applied to the bigger table before the decomposition might be lost when we have the decomposition. And the reason is that these functional dependencies involve attributes that are now spread across tables, so we lost them. So this is a bit sad, but actually it's quite a good compromise to make. Now, there are people who really insist on the preservation of the dependencies and on the lossless join, so they would sacrifice the update anomalies instead. Then you don't use the Boyce code normal form, you use the third normal form, for example. So the third normal form would give you the lossless join and the dependency preserving, but you might have update anomalies with the third normal form. All right. But of course, the second and third normal form, I didn't annoy you too much with that. I just had one slide with the idea that the second is less demanding than the third, and the third is less demanding than Boyce code. And that's why the Boyce code normal form, sometimes it's called the 3.5 normal form, because it's in between the third and the fourth. All right, so this is about this impossibility triangle that you won't get the three at the same time. Then we saw that this whole system, PostgreSQL, is rarely used alone. Typically, it's behind a website. You have a web shop or whatever a business that you're running, and you have servers that have a website, front end. You have customers on the website, and in the background, the database is running with the data. We saw that when you have customers on your website, if it takes 10 minutes to load a page, they will just go to the competition. So you need to make sure that when you look up things in the database, it's almost instant, just a few milliseconds. And we saw that there is a way to do that with indices. Indices are one of the secret recipes in relational database systems that add some additional data structures to the database that accelerate the execution of the queries. And this is an example of a data structure. It's called the B+3, with the idea that you don't need to look at all the data. When you look for something, you just look at something that is logarithmic in the number of data, logarithmic complexity. In that case, if you looked at everything, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places to look at. But you see that with the beauty of binary search, you only need to look at 4 of 11, right? So this is much faster than having to scan through everything. So that's the idea of indices. So we looked at hash indices that are good at point queries when you look for a specific value. And we looked at B+3 indices, which also work well, but they also allow intervals, right? If you query for a specific interval of values, then the B+3 will work. What we also saw is that tables are only one particular shape of data. It's actually one of the easiest one for human beings to learn, but there are others. There are also trees, there are also graphs, there is also unstructured text. Now with ChatGPT, we're quite good actually at handling that. And we also have cubes. And in fact, we did look into cubes at the end of the semester. Trees and graphs, this is big data. So we'll look at trees in big data for engineers a lot. And text, that's information retrieval, which is yet another lecture for bachelors in computer science. So with cubes, the nice things we can do is slicing and dicing. That's something that didn't exist in the relational model for tables, but we can slice and dice cubes, right? And then we can beautifully display the data like this. You can do it with spreadsheet software. It's called the pivot table feature. So you can just import a CSV file and play around by dragging and dropping the dimensions, and you can build views like this. We saw that, again, because of data independence, you have a choice on how to implement it, right? And there's two competing implementations for data cubes. One is called rollup on top of a relational database management system, but then the relational database management system acts as a physical level, right? For the cubes, then it's the cubes that are logical and the tables are then physical. And another way of doing that is called molap. M is for memory. It's the idea that you don't store the cubes in tables anymore. You just store them in some native structures in memory, highly optimized, and that's called molap. Then you don't even have any SQL on the physical layer anymore. All right. Then we saw that for the rollup implementation, you can store the cube as a facts table. And the idea is that every little cube, so in that case, there's 27 little cubes you can see in here in that cube. So you would store it as a relational table with 27 rows, records, and every record corresponds to one of these little cubes that are in the big cube. So every column is a dimension, and then at the end, you have the value for that particular combination of dimensions. We saw that around the fact table, you can have satellite tables, but now that joins have no secrets for you, it's probably becoming natural. And for the people who are crazy about being in the 7th or 8th normal form and so on, I'm joking, they don't exist, 7 and 8. But anyway, you can normalize and normalize and normalize and get even more tables. And then that's called the snowflake schema, right? If you only have one level of satellite tables, that's called the star schema. All right, then I showed you that you can also denormalize fact tables with multiple dimensions. And the way you see that is that there's functional dependencies in there. For example, you have the products dimension, but we also put the product brand in there. And there is a dependency from the products to the brand. All right, and there is a dependency also from the quarter to the year and so on. All right. But what I showed you is that if you do the rollup way, if you do it the rollup way, then you can use SQL to query the data that you need in order to construct the view. SQL will not be able to construct the view, but it will give you the data, the numbers to put in there. So we saw that there is a PostgreSQL extension called group by cube, and group by cube is going to be able to get you the data for a view like this, where you have two dimensions, that's the dicing dimensions, and you have a subtotal on the rows and a subtotal on the columns, and a grand total in the bottom right, and group by cube will prepare all the data you need for that. The other one, besides group by cube, is group by rollup. And group by rollup allows you to do these things. It's when you have these L shapes here with a hierarchy of values in the dimensions. Here I did it with the quarters and the years. And then you use group by rollup, and it will get you the data in that case for one row of that view, for Peter, for example. I didn't show you how to both do a rollup and a cube because that would be much more complex, right? I only said for the simple case of a cube and for the simple case of a rollup with just one dimension. Okay. Then we looked at hardware and just making sure you have general knowledge on the hardware, the idea is that you have the disks, of course, on your laptops, but you also have the memory. The memory is what you lose when you shut down the computer. Then there is the cache on the CPU, which is even faster, but it's extremely expensive because of that. So you cannot have too much of it. It's super close to the CPU. And then we have the super cheap storage level with tapes. This is the cheapest you can ever get to put the data on tapes. But you just have to wait until you get the data because it's little robots in these places that go get the tapes when you need them, right? So it might take a few hours or a day in order to get your data there. Okay, and above is super expensive. Below it's super cheap per byte. Above, it's super fast. Below, it's super slow. Above, it's not so much data that usually is, but below, there's a lot of data, right? So there is this whole hierarchy of all the places that you can actually store bytes of data. Okay, that actually brings us to the exam. So everything that we've covered in the lecture is exam material. So there are the slides, there are the recordings on YouTube, there is the textbook that every week there was a specific part of the textbook to read. So this is also very important. It also is an opportunity to have the same material explained by somebody else. Maybe that gives you a different perspective. Then we have the theoretical exercises prepared by the TA team. We have the practical exercises that you've been doing during the semester, the clicker questions, the quizzes. Of course, the clicker questions and the quizzes, the exam questions will be much more constrained and precise, right? In the clicker questions and in the quizzes, the goal is to trigger you to learn and work and do a bit of research and so on. So it's sometimes a bit more lax than the exam questions. So you don't have to worry about that. All right, so these are all of these places. I strongly encourage you to again go through that material when you prepare for the exam. On exam day, it will be done on a computer. So we have exam rooms at ETH with computers. Each one of you gets a computer. It's Windows on it. And on that computer, you will have a browser. It's called the Safe Exam browser with Moodle on it. And the exam will be in Moodle. It will consist of at most 60 questions, 60 graded questions, multiple choice, asking you to put some text in a cell. And it's going to facilitate the grading also for more fairness. And it allows us to also spend more time on double checking everything. You will also have an installation of PostgreSQL on the same computer, and you will have Jupyter notebooks. So you'll be able to just type SQL and query data on that computer. The database is already installed. It's already imported. You don't have to worry about that. It will just be there. You will have a notebook that already has a few queries to get you started. So all you need to do is click through, and then you can write your own queries. We will give you that ahead of the semester. We'll tell you exactly what database you will have. We'll even give you the notebook that you are going to have. It will be provided to you. This is with this exam magic box, right? So there is an exam magic box with all the past exam data that will be in there, all the past notebooks as well, and all the past exam PDFs. But just so you know, on exam day, there will only be the data of the exam. We don't have the data of the other exams, only that of the exam, so that you can focus on that one. We are looking, because there was a popular request, I'm not sure if it was also in this course, but in the other course, Big Data, there was a popular request to include in the exam environment some documentation. So just to feel the atmosphere, who here would feel more comfortable if there would be, for example, the complete PostgreSQL documentation in there with the SQL syntax? I see a lot of raised hands. Who would get scared having that documentation? Let me ask the question again, telling you that the PDF is 2,500 pages. Who would be scared by that? So it has a table of content, right? You can navigate and so on. Yes? No, it doesn't. We just add the documentation and that's it. But it doesn't change anything to the exam. right? So I feel that since many of you seem to want this, we'll try. I cannot promise at that point, but we'll try to see how we can add the complete PDF of the, it's the same as the PostgreSQL documentation that you see online. And we'll try to include it either in the Moodle or as a file on the disk that you can open with Preview. Do we have a question on Zoom?
Someone asked about
the SQL cheat sheet is that's the Jupyter notebook, right? This one you will have on exam day, and we show it to you in advance. So you will have it in advance. This will be exactly the same thing you'll have on exam day, right? But since you have the entire documentation, you just have you would have access to the entire syntax. Okay. So we'll confirm with you if we're able to provide that entire documentation, then we'll let you know that you will have it, and hopefully that reduces your stress. Okay, but again, it doesn't mean that because there's the documentation, we'll ask more complicated questions. That's not how it is, right? It's just there, to reduce your stress. You can look it up if you need it, and so on. Okay. Now, just so you know, there is big data for engineers in Spring. Who right now feels like they would like to attend it? Okay. Oh, that's awesome. Yes, so I see some of you in Spring. So just so you have an outlook of that, a bit of an advertisement. There's a lot of things that happened in the 2000s after the relational tables. We have key value stores, triple stores, graph document stores, column stores. And a lot has happened in volume, variety, and velocity, which has the 3 V's of big data. So more data, more various data, and faster data. So in fact, there's so much data that we are running out of zeros every couple of decades, and Rona and Quetta are actually quite new. I think it was added last year, and probably we're going to have even more, maybe in 20 years, they will figure out that it still doesn't suffice. But anyway, just to show you how crazy it is with the scale of data that we are dealing with, and why we have a problem, because otherwise we wouldn't need big data. We could just use PostgreSQL and that's it, right? But why cannot we use PostgreSQL? Well, it has to do with capacity, throughput, and latency and how they evolve. Capacity is how much can we store? For example, 20 gigabytes on a hard drive, or 20 terabytes maybe today. How fast can we transmit data? Maybe I can read my data 100 megabytes per second from the disk. That's the speed at which I read. And then there is the latency, which is how much do I need to wait until I receive the data, right? So this is for mechanical disk is because there's something rotating. And so you need a bit of time until the reading head actually reaches the data that you want to read. So if you look at these 3 things, how they evolved across 70 years. So we start in 1956, right? Even I wasn't born in that year. And look at this. This was the best commercially available computer. It has a hard drive of incredible capacity of 5 megabytes with a throughput of 12.5 kilobytes per second, a latency of 6 milliseconds. Why? Because it's enormous. It's like 1 meter 70 times 1 meter 5 and 70 centimeters for 5 megabytes. So this is what we had in 1956, and that was considered the best of the best at the time of what you could have. Now, if we go a bit into the future, our present, this is, oh, that's just a picture of what's inside. So these disks that actually rotate. Now, this is what we have today. And in fact, it's so small that I have to zoom in, right? This is a hard drive. This is what you have in your laptops. So the largest one that I found today, but it keeps increasing, is 22 terabytes. It can read 291 megabytes per second, and it just needs 3 milliseconds. And the dimension is like this, right? 20 times 10 centimeters. There's even smaller ones. And there's also even better ones that have flash drives that are even faster than that. But the reason we still use mechanical drives a lot is because they are cheaper. So if you store a lot of data, we actually like this kind of drives. All right, now let's look at the evolution of capacity, throughput, and latency between this here, and this. This is how it evolved. Capacity, throughput, latency. And I'm not going to click to make the throughput and latency appear. They're already here, right? So the capacity evolved like by a factor of 17 trillion. There's 12 zeros in there, 17 trillion. But the throughput, the speed at which you can read, only improved by 23,000. That's ridiculous. That's ridiculous. And the latency only improved, meaning that it went lower by a factor of 250. So what that means is that the space we have to store data, we have a lot of space, incredible lot of space, but we can just not read it fast enough. We basically were not able to read it fast enough. It's just a logarithmic scale. Just to give you an impression, imagine that instead of the computers, I'm using a book. Today, I could have a book with 600,000 words. For example, that book right here. Let's say the speed at which I read is 1,000 words per minute. That sounds quite reasonable. And the latency maybe is 1 minute. It's stand up, going to the shelf, get the book, and come back to your seats and find the page, right? So maybe you need 1 minute for that. That's the latency. Now imagine that we go 2 centuries into the future. That's generous, right? Because for the drives, it was only 70 years for that. But let's go 2 centuries into the future. So today I can read the book in 10 hours. If I go to the future and I have exactly the same evolution, so I multiply the number of words with 17 trillion and the number of words per minute only with 23,000. Now it's going to take me 846 years to finish the book. Do you see how crazy it is? And the idea here is we are in big trouble. This is why we have to find another solution in order to deal with so much data, right? We cannot wait for 846 years when we want the result of a query, right? That just doesn't work. So what we do is we parallelize. The idea is that instead of reading the book just once, we just spread it to 200 billion people, maybe on Facebook or TikTok, we'll find volunteers. And then we can actually read it all in 10 hours. We just distributed it over plenty of different people. And in fact, that's exactly what we do in big data. We have a data center, we have thousands of machines, tens of thousands of machines. There are even companies that have thousands of data centers. That's telling you the number of computers that there are in there. And so we read in parallel, and this is the secret of big data in order to be able to manage that much data faster. And the second secret, we'll explain it in big data for engineers, it's batch processing. It's the idea that you don't process record by record, but you process maybe 1 million records at the same time to be a bit more efficient, right? Okay. And so as a consequence, big data basically is there because we have troubles because of the discrepancy in the evolution of capacity, throughput, and latency. And so we needed to invent new technologies to store and manage and analyze the data. Right. So there's applications in astronomy. DNA also in biology is very interesting at the moment. In fact, there are people who even manage to execute SQL on top of DNA. So it might take a while to actually realize what that actually means, but they really store the relational tables on top of the DNA and were able to execute SQL on a molecular level on it. So this is an example of data independence, because you don't have to have it on top of a computer. You can also have SQL on top of DNA. So in that lecture, we looked at databases. There's also machine learning lectures. Who took machine learning lectures? Some of you, right? So it's complementary to this. So the relational tables, basically, you could consider them as the input of a machine learning algorithm, at least the classical ones, where you have the features and the labels in the columns, then you feed it into machine learning and so on. But of course, I didn't touch that during this semester. In big data, we are going to be looking at things like cloud storage, S3, Amazon, HDFS, Hadoop, XML, JSON, HBase, Bigtable, XML and JSON schema, MapReduce, Yarn, Spark, MongoDB, JSONic, and so on. Who already heard some of these words somewhere, right? A lot of you, right? So we look into all of that in big data. But for now, I would like to issue a big thank you to the TA team who are amazing this semester. They prepared the exercises. Right now, they're preparing the exam for you. So what I would like now is both on Zoom and in the lecture hall, an enormous round of applause for the TAs so that they can hear you also on this. They're right here in the front. We have Bowen, Marco, and Alexandre. All right. So thank you very much for the great work this semester. And some of you I'll have also in big data for engineers in the next semester. So you'll see them again next semester. All right, so what do we do now? Maybe before the break, I'll explain to you the rules of the game that we are going to play. And right after the break, we are actually going to play the game. So who knows Eiskagerhundert? on TV. Okay, so some of you. The idea is that at the beginning of the game, everybody who wants to play, you will all stand up. Then I'll ask you questions on Twitter in the app, the usual one, and you will answer with your smartphones and machines. And then it's based on trust. I trust you. Once you get a question wrong, you need to sit down, and then we'll see who survives the longest until we have a single survivor, a single champion. You can still continue to answer the questions. Of course, even if you're seated, you can continue to participate, but just in parallel, we'll look for this champion. For every question, we'll also ask for a collective answer by the TA team right after you've given your answers when we reveal the solution. And we'll see if the TA team manages to survive longer than the longest of you, right? So you have an opportunity to beat the TA team, right? Yes? Just one round, one big round, starting with everybody, and I have 10 or 15 questions. Yeah, but it's a single big round. But you can still participate again, because otherwise it's frustrating, right? You lose. And so you can really continue to participate on Clicker and answer the questions, but we'll just try to find the champion. Right? Yes? How is? Twitter. Oh, I don't involve Twitter. I involve Clicker, the Clicker app. Yeah. No, the Clicker app, that's the Edu app designed at ETH. All right, I couldn't anyway because of data protection and because we cannot expect you to have accounts. So Clicker. All right, so we'll take the break. So it's almost 11, and so at 11:15 we just go ahead and play the game. And on Zoom you will also be able to play. We'll do it with the raise hands, right? So you can also participate on Zoom. But of course, if the champion is in the lecture hall, they get the chocolate. If you're on Zoom, you cannot get the chocolate, right? That's the difference.